Yes.
Okay, good. Okay, so the topic for today is threads and RPC. So it's our second lecture in 6824. And we're going to mostly look at threads and RPC in the context of Go, the programming language that we're using in the labs. And in fact, most of this lecture is really tailored towards helping you do Go programming for the labs. So all of you have done hopefully the tutorial and the crawler exercise, which we'll discuss in quite a bit of detail later in the lecture. But before jumping into the details, let me do a little bit more of cold calling to sort of break the ice and get people to ask questions. So maybe you can answer the question, where are you and how did you enjoy the tutorial? What is your first impressions of Go? Maybe how about Even Veldman?
Hi, folks. I'm Batman. I'm in Newton, which is on the outskirts of Greater Boston. Tutorial was interesting. It was my first exposure to, a non-object oriented language. So it's kind of a change in framework that was interesting to adapt to.
Okay, how about Brendan Wong? Brendan, are you there?
Yeah, sorry, I was just finding the unmute button. Sorry, what was the question? I just joined.
Oh, where are you and what is your first impressions of Go?
Yeah, I had used Go before for an internship, but it's my first time actually dealing with the concurrency stuff, like really working with Go routines. So kind of initially it was like tricky to think through like as soon as the main thread ends, all the Go routines are ended. So kind of working through those early kind of conceptual issues, but it's interesting to kind of think through.
How about Connor Prisby? Connor, are you there? Oh, yeah, maybe try somebody else. Dory Shen.
Hi, I'm in Cambridge right now, and I found Go to be really pretty interesting. I thought through the first part of the tutorial, I like learning about the for loops and the ways they do for loops. I thought that was pretty interesting, and the way it's kind of structured. I think I like the threads in I found to be a little bit more difficult about when it ended and when sometimes the function would end before all the routines ended. Yeah. So that was interesting to think about, and I learned more about that. So it's pretty cool. I liked it.
Good. Well, I hope all of you are going to have a very positive experience with Go in this semester. So let me say a little bit why Go. In principle, there are a lot of programming languages that you could have used for doing distributed programming, and Go is absolutely not the only one. But there's some reasons why we chose Go in 824. First of all, it has good support for threads and RPC, and those two are very important for distributed programming. So it makes sense to Go is a good match for that. Second reason that we like it a lot is it has a garbage collector, and if you do a shared memory style parallelism where multiple threads share a structure or a variable, then having a garbage collector is nice, because then the threads don't have to decide who's the last thread that actually has a reference to this memory and should therefore deallocate it. The garbage collector just takes care of all those problems. So that's convenient. It's type safe. It is simple. It's a reasonable simple programming language, quite easy to learn. And in fact, hopefully you got that experience with doing the Go tutorial. That once you do the Go tutorial, you got most of Go. And then finally, it actually has a compiler, so it's compiled. Unlike Python, or actually the compiler produces executable code, and so the runtime overhead is not as large. I guess sort of the final reason why 824 is in Go is because I enjoy writing Go programs, and so that may be also an important reason. So what I'm going to do is I'm going to talk a little bit about threads in general, RPC in general, and talk a little bit about different aspects of programming with threads. Some of that is pre-tutorial. If you have seen this before, my apologies. I'm going to go reasonably quickly through it. It's definitely not a comprehensive introduction to concurrent programming, but just hopefully enough to remind you what the issues are and what you should look out for. And we'll hopefully spend some time, quite a bit of time on the crawler. And so I'll share you the solution. I have two solutions, one using channels and one's using mutexes, and we'll go through both of them. Any questions so far before I sort of dive in? Okay, let me get started with threads. So thread is basically shorthand of thread of execution. In Go, a thread is called a Go routine, but everybody else basically in the world calls a thread a thread. And so the way to think about it is that, like, when you do Go run, now the Go will create a process, on your operating system, and inside of that process is the Go runtime system. And when Go starts, it actually has one thread of execution, the main thread. But then it has primitives to create new threads. And so you can think about this as many threads of execution, running in parallel. And you can think about a single thread as basically sort of a sequential program running. So the program has a program counter, has its own stack, it has its own set of registers. And so this behaves like a sequential program. Like you can execute instruction 1, then instruction 2, then instruction 3, then 4. May make a procedure call, allocate memory on the stack, return from a procedure call, do a recursive call, all sort of your standard sequential type of programming. It's just like happens as a sequential thread, basically. The interesting thing is that the threads may actually share memory with other threads. So since all the threads are running in the same address space, the same operating system address space, or the same process address space, they can actually share memory. So one thread can write to location, say, 10, and then another thread can actually read that location 10. And so that way they can actually communicate information. One way to think about a thread too is to think about it as a sort of an abstraction that supported by the runtime, and the runtime has a number of operations on a thread. So one operation, we've seen many times, if you've seen how many times, is to actually start a thread, to create a thread. This is the Go syntax, the Go keyword. A thread can exit, and generally this just means the exit action sort of implicit, like when the thread returns from its if you create a function using Go, the Go keyword, and you return out of a function, then implicitly the thread actually exits. The Go runtime also has a couple other sort of under the hoods operations, if you will. One, it can actually stop a thread. So, for example, if a thread writes to a channel and there's no reader on the channel yet, then the thread might get blocked, and so the Go runtime sort of stops the thread, puts it aside, so that it can actually run another thread on the processor, and then maybe later on resumes that thread. So there's a sort of a third, final primitive that actually is to resume threads. And really, what it means to stop and resume a thread is basically taking the state of the thread, like the program counter, the stack pointer, and the registers, and put it inside, run another, thread on the processor, and then at some point, decide to resume the processor, which means basically loading the program counter, the stack pointer, and the registers back into the processor so that it can start running. So that's sort of a very mechanical view of what a thread is. So why you have threads in the first place? And that seems like an important point to discuss. Because in some ways, the only thing that threads do is make your life more complicated as a programmer. Like writing sequential code is actually just easier than writing parallel code. And the main reason to have it, and the main reason we care a lot about it in 6824, is to express a concurrency. And sort of three different, sort of two or three different types of concurrency that we actually care about. So we think about our, process, we got our runtime, with our threads running. One type of concurrency that we care a lot about is I/O concurrency. So one of these threads, that is running here, might actually make a network call, connect to another machine on the network, to implement a distributed application, like MapReduce. And as it makes that call, it's going to be blocked, waiting for a response. And while it's blocked, waiting for a response, it'd be really nice to actually run some other threads, so that so that we can get more work done. Or, for example, if we want to issue multiple requests to multiple machines, sort of roughly in parallel, we could just do that. We fire off one go routine, then we fire another go routine, another go routine, that all kind of send and make connections to other remote machines. That's one reason that we care a lot about it, I/O concurrency. The second reason that we care about it is, it allows for multi-core parallelism. So we have, multiple cores in our, computer or processor. Then, we can have one thread running on one go routine running on one core, and another thread or another go routine running on another core, just straight in parallel. And for example, if we implement a key value service, then we could process maybe requests for different keys in the key value service on different cores completely in parallel, increasing our throughput. So those are the sort of two main reasons that we care a lot about concurrency by threads. There's a sort of a third reason, there's a little bit of convenience. So there's going to be a number of cases in the lab, for example, where we want to have something happen periodically, like maybe every second or every 200 milliseconds. And we can just launch a thread for that or a go routine for that. It just sleeps for 200 milliseconds, does what it needs to do, and then it goes back to sleep for 200 milliseconds. And so it's convenient to sort of have these sort of background activities that need to be done periodically, and you can express that using threads. Of course, you can express it in other ways, but threads are actually convenient. Another question that comes up often, and I think it came up in some of the lecture questions today, like how many threads should you create? And I think the Go designers, the way they want you to think about it is that you should create as many threads as you need. They're definitely not free. They tie up some memory because you have to have a stack. There's some performance overhead with starting them, but you should think about them as very lightweight. And so you should be encouraging, or you're encouraged to create threads as you go. Any questions about sort of this basic reason why to have threads? Okay, let me then, as I mentioned earlier, threads actually have challenges. Programming with threads has challenges. So let me talk a little bit about the challenges. I'm not going to go in great amount of depth here. I assume that they will make sense, and they will become more clear if we look at some of the examples. And probably the main reason that threads actually are challenging is that you can have race conditions. And just like a basic example of a race condition, let's say you have two threads. Here's T1. Use T2, and they share a variable n. Let's say the initial value is 0, and they both execute, both threads execute a statement to perform, as the increment n by 1. And of course, you might think that statement is an atomic operation or like something that is indivisible, but it isn't, right? I mean, the Go statement that gets compiled, to whatever instructions the processor is executing, and so we cannot assume that that's an atomic instruction. And in fact, it consists of basically like a load, to which stores the content of n into a register, then increment the register, and then store the register back into memory. And so if you're very unlucky, if the two threads basically try to both execute this particular instruction, then we can have a very unfortunate sequence of events where like both threads perform the load instruction, load the variable in registered, let's say R0, here also in R0. They increment it, so R0 becomes 1, and then they write it back, to, they do a store instruction that actually results, stores the results back into the variable n in memory. And so if this happens at this particular, in this scenario where this happens like truly concurrently, what is the value of n after these two threads did both an increment?
Just one.
Yeah, it's 1. And what is this value supposed to be, or what do we expect it to be?
2.
Yeah, you expect it to be 2, right? And so 1 is definitely not equal to 2, and that's a bug. And so, and this is like, the sort of the heart of race conditions, which is that, if in an unfortunate sequence of events where threads share, state, the updates actually might not really be reflected correctly. And of course, most of the time this will work out fine, because you just have to be in this sort of very, this very specific case before it shows up. So for example, I think one of you reported like, oh, I didn't have my locks or my race, my locks in order, and oh, my program just worked fine. And that is actually the real issue with race conditions. They typically just work fine, but sometimes it goes wrong. So the two ways to address race conditions. The first way is to avoid sharing. So don't share variables. And this is one style of programming that Go encourages by using channels. Channels, you just communicate values, but you don't really directly share memory. So that's one way of doing it. Another, so avoid sharing is one big approach. The other approach is actually to use locks. To make a sequence of instructions an atomic operation. And we'll talk a lot more about that in a second. One of the things that I want to point out that is really cool about what is a useful tool is Go actually has a race detector. And most of the labs that you were doing will encourage you to basically run Go using the -race flag, and that will actually not catch every possible race, but it does an extremely good job of actually identifying races. And so you should, by default, run Go with the race detector enabled. Okay, so that's one challenge with threads. The second challenge with threads is actually coordination. So it's often the case that one has to, one thread must wait on another thread before something is accomplished. A number of the Go exercises in the tutorial, had that kind of form. And there's two ways, Go actually has two primitives for dealing with that. One, again, channels. Channels basically allow you to communicate and to coordinate at the same time, or which I'll talk a little bit later about, condition variables. And both can be useful. I'll talk a little bit more about that. And then finally, sort of the final challenge, big sort of conceptual challenge is you can get deadlock. So if one thread waits on, like T1 waits on T2 and T2 waits on T1, before, for example, it releases a lock or before some other sequencing, you can basically sort of what I call deadly embrace, where both are waiting on the other, and as a result, nothing makes forward progress. A trivial way of getting, say, deadlock in Go would be like you have a single thread, there's no other threads at all, and you're right to a channel. And that will block that one thread until somebody else, some other thread reads from the channel. But if there's no other thread at all, that will result in a deadlock. Right? This is like the simplest possible deadlock possible. And Go actually will catch this case and will raise a runtime error saying like, no threads can run, you have a deadlock. But there can be more complicated deadlocks, where involving multiple threads. And as you're going through the labs in the semester, I'm sure you will run into some. So take a little bit of a step back here and think about, Go for, these challenges that I just talked about. Roughly speaking, Go has sort of two plans to handle these concurrency challenges. And one plan is, basically around channels. And there's another plan basically around locks and condition variables. And the way I think about it, some people are quite dogmatic about this and think one plan is better than the other plan. My general approach here is like I usually want the plan that is most suitable for the case that I'm looking at or that I'm running into. And generally, I have no sharing. And basically, I need 2 threads to communicate, but I don't really share any memory. I tend to use channels. If there are 2 threads actually do share memory, because it's convenient to share memory, for example, I write a key value servers and I want to share the key value table, then I use locks and condition variables. And so, my general approach is not to be dogmatic and to take whatever approach that actually is most convenient for the problem at hand. The tutorial does a pretty good job of actually teaching you about channels, mentions locks, doesn't say much about condition variables. So I think it's worthwhile to talk a little bit about condition variables to make sure that you're aware that they exist. And I'm going to do that using a tiny little example to sort of illustrate the issues. And the tiny little example is we have a sort of a little bit inspired. It's a little bit inspired by the labs. We have a thread T1, and T1 needs to collect a number of votes, from remote machines. And for example, it needs to decide that it has a majority, so that it actually can proceed to commit, some value. And you'll see that later in, like this shows up in the Raft lab as one of the sort of primitives that you need. And so to do that, the T1 will fork, other threads, like say T2. And T2 amazingly does something expensive, like, talk to some remote machine to actually get its vote. And then, reports back, that vote to T1, and T1 basically needs to collect all the votes, add them up, and then as soon as there's majority, then, declare sort of victory. So this is a pretty straightforward, simple program, but it gives you a little bit of, allows me to illustrate you a couple of issues. So I'm going to switch to another screen. Can everybody see this? Here I have a very simple implementation of this program, the vote thing. And again, it's a little bit of a toy example, but just hopefully gets the points across. The 2 variables shared here, count and finished. Count counts the number of votes. Finish, counts when we're done. So there's a loop going for 10, creating launching an anonymous function, and an anonymous function, concurrently, calls this function request vote. And request vote basically, simulates, doing a long, expensive operation on some remote machine, and the way it simulates it is by just going to sleep. So it blocks for a little while, then it returns, and then if the returns voted is yes, then the count goes up, and we count the fact that actually we had one more thread voting, and then we're done. And so that's so we fork off 10 threads. Each are doing the request vote and report the result, and then at the end we'll check if the count is smaller than 5. We know that we failed. We lost the election, and if we have votes equal or larger than 5, we basically won the election. Right? So this is sort of the simple, it's a very simple program. Does it all make sense? Let me run it just for the kicks. And we run it a couple times. Sometimes we lose, sometimes we win. It makes sense. And so this program looks, working and correct. Is it actually correct?
Sorry, was the question whether this program is actually correct?
Yeah, it seems to produce results.
I think there's a race condition, isn't there? Like you have all of these different threads incrementing the count and finished variables.
Yeah.
And it's also it's not clear to me that finished necessarily always reaches 10. Is it possible that it doesn't?
Let me take these one by one and just go over your first point, which is the one I was after. Clear this has the fact, we have two variables here, correct? Count and finished. They're accessed by different Go routines. So this is immediately a red flag. There could be a serious problem here. Right? As soon as you have a variable that is accessed or modified and by two different Go routines, there's got to be a problem. And so it's interesting to run the Go race detector and see if it actually catches it. Right? And as you expected, the race detector tells you exactly, there is indeed, some problems here with this program, and list the line numbers, where things actually can go wrong. So that gives you actually a pretty good clue that something is not up to snuff in this program. And so we're going to repair it in small steps, and that will hopefully shed some more light on concurrent programming. So let me, here's my second solution to this program. And in this case, I'll talk about channels in a little bit later because I wanted to illustrate the locks and condition variables first because that got less emphasis in the tutorial. So, simple solution, with Go, correct, you introduce a lock. The lock is completely independent of the variables, and you follow some convention, which says well, this lock mu protects count and finish. And so whenever you access count and finish, basically you have to wrap that into a lock and an unlock statement. And so here we see two, this is the Go function that runs concurrently, and after the request vote, it's about to update the vote and finish. So we take a lock out, and then Go has this nice feature called the defer statement that if you exit the basic block, it will run the function that is declared by the defer, or that is after the keyword deferred. And so this means when we leave the Go function here, we'll automatically unlock. And this is convenient because then you won't forget to unlock. And so it's nice to do that right at the point where you do the lock. And so you can write immediately defer unlock, and then you don't have to worry about if there are multiple exit paths out of a Go routine or out of a function that you forget to unlock. So now, we're basically in a critical section where we hold the lock, we update vote and count, and then of course the function returns and unlocks automatically. And then similarly at the end, we gotta every time we access count and finish, since they're shared, we need to surround it with locks. And then here's a simple way of doing it. We could have written defer unlock here too in the body, but that would have been fine. All right. So we can actually run this program. Let's see. And so we run it. The race detector seems to be happy. So hopefully we'll have a better program. All right.
So I just have a question here about scoping.
Yeah.
So it seems that when we have the anonymous function, then we have this mu, and we have the count, and we have the finished, and it seems that the anonymous function has access to variables that were defined outside of the function. So how do scoping rules work?
Yeah, any with an anonymous function, any variable that's used inside of the function that's not declared inside of the function basically points to variables outside of the outer scope, so statically scoped.
What about the scope of the mutex? How many times do you have to declare that, and what's the scope of it? I guess
the scope of the defer statement is this block, one basic block. So
no, I mean when you actually declare the mutex data structure, I guess.
Oh, yeah, it's like any other variable. It has the same scope as finished or count.
So it applies to any variable declared in the rest of the.
Yeah, the way to think about it is that the mutex is not directly associated with any variable. It's just a lock. It's like a name, and it's up to you as a programmer to decide what that lock protects. So they're two independent concepts.
What happens if you use I in the Go routine? That wouldn't work, right? You need to pass that in.
Yeah. So that's a good question, and then a number of you asked that for email too. So what happens to if we use I here? We'll do something with it, whatever. Count is I. Is this a good plan or not? What value of I will we be using when this thread actually happens to run? If it Go starts to function, it will run at some point. Now, what value of I will we be using?
whatever I happens to be at the time, which is being changed by the for loop outside.
Yeah, correct. So, and so this is not so great. That's probably not what we intended, right? We probably intended the I that we, whatever, for that particular loop iteration, right? So how do we want to, if we had to solve that, what would we do?
You could add it as a parameter to the anonymous
Yeah.
function and pass it in so that it gets evaluated when you create the Go routine.
Yeah, correct. So we could write this and then pass it actually in, right? And then a point, what happens then at the point we actually create the Go routine, I is being captured and then passed in. Okay?
Can I ask how are the local variables allocated? Like if count and finished are like local variables, wouldn't they like be destroyed after the main function exits? Or like if this wasn't main, but like another function, what if like the containing function exited before the Go routine?
Yeah, they're in principle allocated in the stack. And presumably the other functions have just memory addresses, references to them. And so it's indeed the case is main returns, then these, these stack allocated variables are gone. So typically what you will see is that in a Go program, you would allocate them in, on the heap, using new, like if you make a new struct or whatever.
So would you get a segmentation fault then, or would it just?
You would get a.
Oh, okay. All right.
I have a question. I don't actually remember if this is the correct way to do it or not, but instead of passing it in, would it be possible to, as the first line in the for loop, do I : equals I? And then you're like, you have a, I don't know how the scoping works within the block of the for loop, because I think that should create a new variable I that the Go routine can access that isn't being updated again, right?
You could do that.
That can help instead of passing it in. It kind of makes it look ugly to me.
Yeah. Okay, well, I like the passing in, but that's another way of doing it. I'll show you an example later. So somebody asked actually, do we get a segmentation fault? We're not immediately going to get a segmentation fault. I should take that back because basically one thread will still hold a reference. And so the garbage collector will not delete the object yet. Right? Only when the last thread actually, only when no thread holds a reference, will the garbage collector delete the object. And this is one of the cool things about having garbage collected language and shared memory programming. You don't have to worry about that scenario. Okay, there's a, yeah.
Could this code deadlock? Because if the Go routines, the first for loop will exit and then the second one will yeah, no, never mind.
Okay. There are definitely some issues that are not ideal yet. So let me actually talk about them. One of them is that this particular loop, it's a little bit annoying, right? This for loop there's nothing else than waiting until count reaches 5 for finished. And the way it does it is by just spinning, right? So it just locks it, looks at the value quickly, unlocks it, and spins around again. So basically it's spinning on the processor, doing really nothing. It'd be nice to express that in a little bit better way so that basically the Go can sort of give up the core and so that another thread can run. And so the way you can do that is using condition variables. And so this is my the next implementation. Or actually, I'll show you one other implementation. Well, one way to do that is a little bit not so nice. Is, for example, and somebody suggested this, is to actually sleep for a little while. So instead of giving up the spinning like crazy, just sleep for sleep for a period and then come back. And of course, the solution will work, but the downside of it is that how long should you sleep? Right? You really would like to be the case that soon, for example, if this guy reaches 5. Then you wake you could wake up this particular the main thread, and so I was jumping ahead a little bit, but so that's what condition variables are for. And here's a solution with condition variables. So we allocated a new condition. Here's a condition variable is allocated. It's associated with this particular lock. We'll see in a second why this is important. And basically the main thread, what it does now, it grabs the log because it needs to grab the log to look at count and finished. Otherwise, there could be erase conditions. And then if the condition is still not true, it just calls wait on this condition variable. And what that does is actually that atomically goes to sleep as well as releasing the lock that is associated with the condition variable. Since mu is actually really associated with the condition variable, can't wait basically unlocks the lock and goes to sleep in an atomic operation. And when it returns, from can't wait, it will actually hold the lock again. So the caller knows for absolutely sure that if can't wait returns, it will actually hold the lock again. And so it's safe again to look at count and finished and then call wait again. Okay. So basically, this thread will go to sleep. And then the go routines that are collecting the votes, same code as before, lock and unlock or defer to unlock. And then when you're done, updating count to finished, there are two primitives on the condition variable. One is signal and one is broadcast. And broadcast basically signal wakes up one waiter and broadcast wakes up all waiters. There's only one waiter here, so we could have used either one of them. And so basically when it reaches 5 at some point, or 10, then so every time finish is incremented, the main thread will be woken up. You can check the condition and then keep going. Okay. And so this is convenient. You can think about condition variables as a coordination primitive, between two different threads. And they're particularly convenient when you're actually using locks, to protect your shared state. So here's the same implementation of this program using channels. And more or less works the same way, except we're of course no locks. But the main thread creates a channel, passes the go routine, the anonymous function that is being created as a separate thread. It writes basically the request vote to the channel. And then the main thread basically blocks here, correct, when it starts reading from the channel. Once it actually gets something is written to the channel, it will unblock, look at the value, and if it's true, add up, and always increment finish. And what's going on here, correct, is we don't need locks because count and finish are not shared. There's only one thread that actually updates count and finish, and that's the main thread. Okay. And this the main sort of the request threads all basically just write to this channel. They write concurrently perhaps to the channel, but the channels is one of the things in Go that actually are thread safe, so multiple threads can actually write to the channel. Any questions about this solution?
What was the thing about like having a buffer for the channel?
Yeah, so normally when you're writing to the channel and nobody's reading from the channel, or no thread is reading from the channel, then the sender will immediately be blocked. You can specify that the channel has a buffer, say, of 10 or 20, and that allows the channel to have multiple values. In 824 labs, I've never used buffered channels, and one of two free times I did it, I regretted it. So in general, I don't use it. But this raises an important point. This program is actually still not very good. So for example, when it doesn't matter in practice in this particular example, but it is not in some of the labs that could bite you. As soon as it reaches count 5, what will happen?
It stops listening for listening to the channel. So any other threads are just going to be blocked.
Yeah. So basically, it means like if the first 5 threads voted yes, then the next 5 threads will be blocked in this channel, correct? They'll be hanging around. And in this case, it won't be a problem because, as most of you guys most observed, like that if the main thread exits, it actually cleans up all the other threads too. But for example, if this be a long-running service, this would be not good, correct? Because basically we're leaking threads here. They're sitting blocked on the side, doing nothing in that channel. And so that's quite inconvenient. And this is something to watch out for. And this showed up in the crawler, I think, for many people. And there's the flip side of this is that if the main thread enters too early before any of the request votes are done, then you also have a problem. And so there's this management of threads that actually is often a tricky issue.
Is there a way to kill the thread without exiting from main?
Well, you could send it a variable or a value on some channel saying like, please exit, but you have to coordinate it yourself. I want to go back to one of the things that actually is cool about condition variables is that in principle, you might think that the same issue exists here, where like this thread actually runs and this thread and it might get blocked. Like for example, if we reach 5, this main thread will proceed doing its thing, while the other guys are still maybe actually sitting in here. But notice these, in this case, they won't be blocked because well, grab the lock, then does its thing, does a broadcast, and the broadcast is actually not a blocking operation. So unlike writing to a channel that is a blocking operation if nobody is listening, the conf broadcast is not a blocking operation. And so this actually works out in this particular program by itself correctly. Okay. Okay, good. Any further questions about these two examples? Just to okay, then let's talk about the crawler. And so the crawler is also a more realistic example of concurrent programming. Yeah, and just to remind you, basically the idea is that you start out with a URL for some web page. You fetch, you fetch the web page. It might have more URLs, and you basically proceed, then fetching those web pages, looking at those URLs, and you keep going. And the idea is to crawl basically the whole internet, for all the web pages that exist. And of course, some URLs might point back to a web page that you already visited, and so the goal is to actually not visit the same web page twice. And so the goal of the exercise is a couple goals that you want to achieve. Right? One is I/O concurrency. The fetch operation is may take a long time. Maybe it's a web page that sits on the other side of the world. Maybe goes over slow networks. And while your sort of one thread is sort of fetching that page, you would like to be able to fetch other pages. Another goal is this correctness goal or performance goal, namely fetch a URL once. And presumably you would also like to exploit multiple cores. If you have multiple cores, you can do them work in parallel. Okay. So what I'd like to do before actually talking about the concurrent solutions first, let me show you a simple serial solution so that we we have something to talk about as a baseline. So, I have 3 solutions in here. So you just run them. Go run. A serial solution, and one with mutexes and one with channels. You see that more or less they produce the same result. 2 found, 1 missing, 2 found. The only difference is that the order of the output is slightly different once in a while, and of course it has to do with concurrency. Okay, so the main function calls serial with the starting URL, the fetcher, and then an empty map. And then the serial solution is basically a sort of standard sequential recursive solution. We'll first check if we already visited the URL that's passed into us. If we did, then we return immediately. Otherwise, we mark it as visit. We'll fetch the URL. That gives us a bunch of new URLs. We look through all the URLs and call basically serial again. Right? And this is your sequential solution as you would expect it. And your goal was to basically write a concurrent version of this. And so what I like to do is actually to make the class a little bit interactive. I want to go switch over to breakout rooms, and what we're going to do is basically put 4 to 5 of you in a single breakout room for about 10 minutes. And I would like you to do is, share your solution with each other and discuss it. So maybe the best way you go about it is that one of you, you get into the room, one of the persons in the room, basically screen shares their solution and discusses, one of the issues that he or she ran into, and other people can comment or share other solutions. And just to get into the discussion and meet some other students in the class. Any questions about that? Okay, good. Let me go back to sharing my screen again. Can everybody see my screen again?
Yeah, looks good.
Good, good. Thank you. Okay, so hopefully that was interesting. And let me, talk about, the solutions that I have. They're posted on the schedule page. If you haven't, you can look concurrently with me if you want to. There's a, let me walk through the mutex version first, and then I'll walk through the channel one second. So here's the mutex one. The mutex one declares a struct, that has both the map and the mutex. And the map needs to be protected by mutex because there's going to be concurrent access to the map. So map by itself is not thread safe. It's up to the programmer to actually make the map thread safe. And the concurrent mutex one works sort of similar to the serial one, except whenever there's shared state, basically takes a lockout. So we'll take the lock, we'll look at if the URL already has been fetched. If it hasn't been fetched, we mark it as now being fetched or hasn't been fetched, and we unlock. And we kept this already value to decide whether we should return or not. And then, this go routine starts fetching a page, gets a bunch of URLs back. And then for every URL back, it creates a new go routine here on this site, passes in the URL that go routine is supposed to fetch and crawl. The only sort of other interesting thing here is that it uses something called a wait group. And wait group is a very convenient primitive to sort of keep track how many threads you still have active and when you can terminate. And this was a sort of a big issue in this particular assignment, that if you terminated too early, then you didn't crawl all the web pages. And so you need to keep track of whether there's still outstanding web pages to be crawled. Sync wait group does it very easily. Basically, every time you call a thread, you call add, and then when the thread terminates, you call done, and you can conveniently do that in the defer statement. And then the main thread that is waiting for all the threads to terminate just calls wait, and wait will return until every thread that was started, or every add one, if all those threads actually have been exited. And so that's the mutex version. And you can think about sync wait as sort of being internally implemented using a condition variable. Okay, let me look at the channel version. So here's the channel version is basically sort of organized as the MapReduce lab, where there's a coordinator and workers. And so we start off creating a coordinator thread. And the way we do that actually is we make a channel, and then we pass that channel into the coordinator. The coordinator, of course, has to start with a URL, the beginning URL. So we need to supply that on the channel. That's the most convenient thing to do, as we'll see in a second. But to send it on the channel, we basically have to create a go routine, because otherwise, we deadlock here. So and this is a typical thing. We create a go routine just to send that value on the channel. So let's look at the coordinator. Here's the coordinator. It doesn't use any locks at all, because the data structures that there's no data structures actually being shared, like fetched. The map that actually keeps track of which URLs has been fetched is actually only accessed within the coordinator. So the coordinator got when we called it initially, it has one URL, it checks the fetch map, and then for every URL, Then it goes basically, cycles through, reads the channel using a range statement. And basically what this does is it just keeps reading the channel and it just grabs the next value, grabs the next value, grabs the next value. So basically it grabs the URL. We know there's one in it because we put it on when we created it. And then for that URL, we sort of roughly do the same thing as the concurrent as the mutex one. We see if the URL has already been fetched. If it hasn't been fetched, then we're done. Otherwise, we'll create a Go worker to actually fetch that URL. And we keep track of how many outstanding workers we have. So n is counting the number of workers, and only when n is 0 do we terminate the coordinator to make sure that basically we have fetched all the web pages that we're supposed to be fetching. So let's look at the worker. Worker basically calls fetch. This of course now happens completely in parallel with any other workers. If it actually fetches some URL from that web page, it basically writes all those URLs to the channel. And so the coordinator will get all those channels through its range statement. And then when it's done, writing all the URL through the channel, then the coordinator or the worker exits, and that will, at some point decrease, n, and then at the end, and that's it basically. Okay, so those are the two solutions. Any questions about these? This is all clear?
There's a question in chat.
Good. Let me get my chat list back up. Okay, so the question is, when CH has a value in it, when all other threads be idle? It is the case that since this is not a buffer channel, there's going to be only one request in the channel at the time. And so all the threads, will be appending to the channel one by one.
But doesn't that make the program sequential? Because no two threads are running in parallel, except the main thread and one.
Well, the fetches will still happen in parallel. And those are presumably the expensive operation, right? Those go out across the internet.
Got it. Thank you.
Okay, let me switch back to my other screen and talk a little bit about RPC, since that's the other tool that you need for the labs. I'm not going to say a ton about it, but just RPC, which stands for Remote Procedure Call. And basically the goal, the goal of an RPC system, like the one that Go has, is to make sort of RPCs behave roughly similar to procedure calls, local procedure calls that you execute on the stack, right? And so the goal is that, for example, if you have a client, in RPC terminology, the caller is typically called the client, and the callee is called the server. Say you have a function, fn, that we're calling with x and y, and then at the server there's the implementation of this function. And so there's a function and whatever x, from a y int, and it returns, whatever, does some computation, but maybe it just returns x plus y. Right? And so what we would sort of like to have happen, or like the model that we would like to sort of ourselves to think about, is that when the client calls this function fn, the RPC system will make sure that there's an corresponding invocation happening on the server side, passes the arguments x and y, to the server. The code runs on the server. It returns a result, say C, and that result is then communicated back to the client, and and then fn will resume, will return, and the client will resume with the x plus y in the value of x plus y in Z, right? And so this looks like, even though the programs are running on different computers, there's not sort of a hard boundary here. It looks like they make sort of regular procedure calls. And we'll see in a second that actually we can make a lot of similarities, so it's possible to make them behave very similar, but we'll see there's also a sort of a fundamental difference, and that actually has to really do with distributed computing. But before getting there, let me first sort of sketch out how you can make this work. And this is sort of roughly, what Go does too. So the way, to think about it is that when the client, so here's our program, and when the client calls the function fn with x and y in it, what it does, it actually calls something that's called a stub. And a stub is basically a local function, called fn, and with the two arguments declared with x and y. And basically what the stub does, you can think of this as a stub procedure. And what the stub procedure basically does is it builds a message, saying, which function needs to be called, the arguments of the function, the types of those arguments, the values of these arguments, et cetera, et cetera. And then what the stub does, actually, it sends it over the network, to a corresponding stub at the server. So the server receives this message, and basically, takes this message and basically unmarshals it. This is the term that's being used to basically convert values from to byte arrays, and from byte arrays back to values, and then calls this function fn at the server. Here's fnx, int blah blah blah. So the stub basically calls the function. The function returns back into the stub. The stub marshals the response value, like z, like x plus y, and sends it back to the client stub, and the client stub is still waiting. So basically the client stub, the way it actually works, it sends out the request and then waits for the response. And so when the response comes back in, it unmarshals, and then returns the value to the client. Right. So basically these two stubs sort of make a remote procedure call look like a regular procedure call. Sort of almost you can't tell. And the key, and these stubs are generally automatically generated. So the compiler, like in the case of the Go compiler, it actually will generate these stubs for you and do the marshalling and unmarshalling of arguments for you. And that's how it goes.
Oh, so when you're doing it from the server to the client, there's also another stub again? Or
Yeah, you basically return back to that first stub. So this stub basically makes a procedure call basically calls the procedure fn. That procedure returns into the stub because the stub called it.
Oh, it's the same stub that it goes in.
Yeah, exactly.
Got it.
Okay. Okay, so let me show you sort of how this plays out inside of Go. And by showing you a very simple key value server. And you'll see, it doesn't look exactly like RPC calls, but it's pretty close. So the typical thing is that, you actually declare, typical convention sort of in Go is that you declare the arguments as structs. And so we're going to implement two procedures, two remote procedures. One is put and one is get. And put is basically, put args is the arguments to the put, and put replies to the response. Similarly, there's a get args with the request, or the arguments to the request get procedure, and a reply. And so let me first look at the server. So here's our two functions, actually the two functions that we're going to be calling on the server. I think I'll skip down for that for a second. So maybe actually, so let me talk about them a little bit. So this is the client side. So the client calls a function get, and what inside of get, this function actually connects to the server. I'll see in a second what that means. It fills in the arguments, it allocates a response, and then it calls this procedure client, it calls call. And you can think about this as a generic stub that basically takes the method that needs to be called on the server and the arguments and the reply. And so call always has three arguments: the method, the argument, and the response. And call internally will marshal the arguments, send the message to the server over the connection, and wait for the response, the reply. When the replies comes in, the reply struct will be filled in by the call stub. And then when that's done, then we return out of the call. And basically put looks exactly the same way. Great. And so on the server side, let's see how that is implemented. The server has a key value map. This is nothing else than a regular Go map. Let me see actually the key value struct. I declared it somewhere. Oh, sorry, it was right above it. So there's a struct called KV that actually has a mutex and a map in it. And the map is like where we're going to do the put and get operations on. And there's another little preamble that you need to sort of write, to sort of set up a server. But here it is. You basically allocate a new server object, and then this is sort of the key operation. RPC register KV will register basically all the methods that are implemented on the KV struct with the RPC server. With one twist, the method only the capital named, only the methods with the capital will actually be recorded. And so basically Go uses capital names to indicate public methods, and a method with a small caps is a private method. So only basically RPC register exports only capitalized methods. So for example, here's a method below, here's our get method, it has a capital letter, and by calling register, that method is now callable by a client that connects to this server. And so the server internally, basically it creates a TCP connection and waits on the TCP connection to get a request or a new connection request for a TCP connection, and then calls RPC servcon to serve that TCP connection. And basically every message that comes in over that connection, it will automatically find the right method that is associated with the message and call that method with the unmarshaled arguments and the unmarshaled reply. So for example, if the client calls get, connects to it, that will makes this connection into existence. And then if the client calls call with a get, then this get function will be run. And as you can see in the get function, first thing it does, it actually takes a lockout, because multiple clients could be calling the server. And so there will be multiple Go routines running at the same time, perhaps invoking get and put. And so they will manipulating the map concurrently. And so we need to make sure that, those that is done in an atomic way. And so therefore we use locks. So the get function looks up the key into the map, looks up the key in the map and returns basically the value. If there's no entry in the map, it will return error, no key. Otherwise, it will return the appropriate value, and that's it. And so on the server side, when this get function returns, it will marshal its response, send the response back to the client. The client will, side of it, will unmarshal it and actually return it to the caller. Okay, so does that make sense? So that's sort of a dirt simple key value server in action. Okay, now I want to make one more point, which is an important point, and that in the end, what's important to think about is what the RPC semantics are under failures. And so there are different types of semantics possible. Something is called at least once. And this all has to do with, like, what does the client do if the server fails? So let's say the client sends the request, the server crashes. And of course, now at some point the client will time out and he just doesn't know whether the operation actually happened or not happened. And at least once RPC semantics means that the client will automatically retry and will keep going until it has executed at least once. The downside, of course, of at least once is that the same operation might be executed multiple times. So, for example, if you do a put, the put might be actually executed multiple times in at least once RPC system. So that's not appropriate for many applications. So another type of semantics that's common in RPC systems is at most once. So the corresponding server request actually executed either 0 times or once, but no more than once. And the way that is typically implemented is by filtering duplicates, and you will actually be doing that in later labs. It could be the case that actually both requests actually come through. Maybe the network was like a temporary petition, and the server actually gets both requests. So the server has to arrange that it detects a resent request and doesn't execute it twice. Now, of course, ideally, you might actually want exactly once, because that's actually what the normal procedure call would be do, right? Like if you call a procedure in your server in a normal sequential program, it actually executes exactly once. It's never possible to be at least once or at most once. And this turns out to be actually very hard to arrange. This requires, you basically have to maintain state on disk, and so that tends to be expensive. And in fact, in practice, very few RPC systems are exactly once. Although in the labs, you're going to build actually one in lab 3. You're going to actually build an RPC system that's basically exactly once. Okay. In practice, Go's RPC system is at most once. So if you do a call and you do the call across the TCP channel will make sure that there are no duplicates, and the RPC system will either execute once or none at all, and then in the case and return an error. And then, of course, the application may retry, but now it's the application's responsibility to deal with the problems of duplication and failed messages. Okay, so here's the sort of the key point, correct? The fact that there are failures basically makes RPCs not identical to procedure calls. So even though that the goal is to make them look as similar as possible, they're actually not identical. And really, the thing that exposes that difference is the failures or the server crashing. Any quick questions about this quick intro for RPC? If not, then I want to stop the lecture here so that people that need to go, or students that need to go to the next class, they can go to the next class. I'll be hanging around, so if there's any more questions, I'd be happy to answer them, and I'll stick around for a little while. In the meantime, enjoy lab 1 and good luck with it.